Hello. So we were in module 3 and last session we have learned an extension of two sample problems, that was non-parametric one-way K-sample ANOVA, and this session we are going to learn non-parametric two-way ANOVA. Okay, so that means this is also an extension, but we are going to cover two types of effects influencing the observations, how to solve this type of problems non-parametrically. Okay, let's start the journey. Under two-way non-parametric ANOVA, we are trying to learn Friedman test, which is most commonly using test for a two-way non-parametric ANOVA. There are few other tests relevant to this study as well, but we are just restricting our attention to Friedman test. Already we have studied non-parametric analog of one-way ANOVA, that is Kruskal-Wallis test. And this lecture discusses non-parametric analog of two-way ANOVA. In two-way ANOVA, as I have already told you, in two-way ANOVA you have to deal with two factors, and both of the factors are influencing the observations. And those two factors generally called as the row and the column factors. Okay, so we will say in the literature of statistics, we will say that this is a row effect and the column effect influencing on the observations. Clear? Now, what would be the data layout? We have data in the form of a two-way layout comprising k rows and n columns. The rows indicate block or subject, and the columns are the treatments or the groups. The observations in different rows or blocks are independent, but the columns are not, because of some unit of association. So, in a nutshell, what we are trying to impart, that means the blocks are, if you can see the array, rectangular array drawn below, you will find out the blocks are placed as a row, and we will say the blocks are independent to each other. That means one block is not influencing the observations placed in other blocks. Clear? On the contrary, if you look at the column of that rectangular array, you will have the treatments or the groups, and these treatments may have some association. Okay? This type of array arrangement is known as complete randomized block design with one observation per cell. So, when I am writing Y11, the first entry will be Y11, then Y12, then Y1n. So, 1 means for the first block. So, the first suffix indicating the first block, while the second suffix indicating the treatment of the observation. Okay. So, when I am saying Yij, that means observation for ith block and receiving the jth treatment. So, I runs from 1 to k, 1, 2, 3, 4 till k, and j runs from 1, 2, 3 till n. We are not necessarily interested in differences among the blocks, but the test statistics to take into account the differences in the block. Okay, so we are interested in the differences of the treatments, whether each treatment has the equal effect on the observations or they have the different effect on the observations. In parametric two-way ANOVA, we assume that the population is normal. So, that is the necessary assumptions one has to undergo while going for parametric two-way analysis of variance, or ANOVA in short. and the variability within each group is roughly the same. That is another assumption, which is otherwise called homoscedastic assumptions. Each observation is affected by column effect as well as the row effect. The classical model for ANOVA is Yij is equal to mu plus beta I plus theta j plus Eij. Now, I am not asking you to remember this classical model. Rather, I am just trying to give you the idea that why this linear model we are taking. Okay, what is the meaning, what is the rationale behind taking such linear format? So, as there are two types of effects already stated, that one is the row effect, another is the column effect. So, mu is a general effect which is common for each of the observation. Clear? Now, beta I is effect due to the ith row or ith block, and theta j effect due to the jth treatment. Clear? And the effects present in every observation but yet not explained, it is denoted by Eij, that is the error. Okay, so that's the error part, which is unexplained part, unexplained effect. Generally, the null hypothesis under two-way ANOVA is whether the column effects, whether the treatment effects are same or not. So, H0 is equal to theta 1 plus theta 2 plus theta 3 till equal to theta n. So, here will be one equality. Okay, clear? When normality assumption violates, we adopt non-parametric two-way ANOVA proposed by Friedman, where each treatment observation within the ith block is replaced by its rank relative to the other observation in the same block. So, suppose you have checked, you know how to check whether a given data set follow normal distribution, Gaussian distribution. I have taught you the QQ plot as well as QQ norm using R. So, by using those tools, once you are sure that is the data set which you are dealing with, they are not following each of the data set, each of the block, they are not following the normal variable, normal that usual mold shaped curve, then what you can do? You can go for the non-parametric counterpart of two-way ANOVA. Generally, we check the null hypothesis in terms of mean effect of the treatments, but when you are switching to the non-parametric two-way ANOVA, this mean effect will be replaced by the median effect of the treatment. I told you median is the non-parametric measure of the central tendency. So, everything, your study of the context will be replaced by the median of the treatment. Let Rij be the rank of treatment J when observed in block I, then Ri1, Ri2, Rin is a permutation of first n integer, and R1j, R2j, Rkj is the set of ranks given to the treatment J in all blocks. Thus, for Friedman test, the data in a k by n table as follows. So, initially it was a array distribution based on the observation y12, y11, y as I have already mentioned. Now, each of the observation will be replaced by the corresponding rank. One point you have to remember, that's an extremely important point while doing the Friedman non-parametric two-way ANOVA. This ranking R11, R12, R1n, the ranking is done within the treatment. Okay? So, that means R11, R21, Rk1 these are within the treatments, these are one block. Okay, this is one treatment and you are making the blockwise ranking. Clear? So remember, as I am saying, we don't form combined sample here. Unlike the Kruskal-Wallis test, in Kruskal-Wallis test, the last lecture, what we have learned, first you have to make the combined sample and on the basis of this combined sample, later rank all the observations. Here we are not doing that. What we are doing? We are making the rank blockwise. Clear? So block 1, rank of first observation, what it will be? R11, then R12, then R1n. So if you add all the ranks, then it will be 1 plus 2 plus 3 plus n, because you have n treatments and you are fixing block and you are ranking those n treatments. Clear? So what will be the rank? The rank will range from 1 to n. That means when you are adding all the ranks, it will result n into n plus 1 by 2. Similarly, for block 2, the row totals will turn to n into n plus 1 by 2. So is for block K. Clear? So we are ranking blockwise. That's what you have to keep in your mind. If the treatment effects are all the same, each expected column total is the same and equals the average column total K into n plus 1 by 2. Now, the test statistic is the sum of the square of the deviation of observed column totals around this mean. The test statistic is S. It is very much similar to the Kruskal-Wallis. Only difference is in Kruskal-Wallis, you are combining all the observations and then you are ranking, and here you are ranking within the treatment. Clear? Fixing the block. So S is equal to summation Rj minus K into n plus 1 by 2 whole square. And if you just, what is Rj? Rj is the rank total of the jth treatment. And if you just split that first sum, that is this sum, by in terms of the rank received in that jth column, then one more sum will pop up and therefore you will have the expression in terms of double summation. Clear? The probability distribution of S can be found. On that basis, table of distribution of S under different K and N is available. Moreover, a linear function of S is defined as Q. And what is Q? Q is equal to 12S divided by Kn into n plus 1. So what actually Q does? Q is another modified version of Friedman statistics. Initially, Friedman has proposed this S, and later on he proposed further Q just to give a known distribution. Clear? So the approximate distribution of Q is chi-square with n minus 1 degrees of freedom. Once again, a quick reminder, what is your n? N is your number of treatment. Clear? So you can see that almost it is similar with Kruskal-Wallis test, one-way ANOVA part. Now the rejection region for a test of equal treatment effect against the alternative that the effects are not all equal with level of significance alpha is Q greater than equal to chi-square n minus 1 alpha. So we reject the null hypothesis if your calculated Q supersede the tabular chi-square value with n minus 1 degrees of freedom. Clear? Let us have one example. Of course, when you are dealing with the manual calculation of Friedman test, it will be lengthy, it will be time consuming, I must say. But okay, let's have some flavor of manual exercise so that you can understand that how R programming goes on, what are the steps within R programming while dealing the same problem by the R setup. Test the claim that at the 5% significance level of all three drugs have same probability distribution in terms of the reaction time over 6 randomly chosen patients, assuming probability distributions differ by the median of reaction time of 3 different drugs. Okay, so these are the subjects. Subjects are taken as the blocks, and each subject, that means each patient, they are undergoing with each of the drug A, drug B and drug C. So these are the 3 levels. And what is the factor here? Factor is treatment. Clear? So blocks are independent, but each block has different effect to the drug. So we cannot recede, we cannot refute the effect of the block. Clear? Okay. So what is my null hypothesis? Null hypothesis is H naught, theta 1 is equal to theta 2 is equal to theta 3. Theta I be the median reaction time. Remember, it should be median. It is a test of location, but what will be the measure of the location? Once again, it will be median. So theta I be the median reaction time of ith drug. Now the step 1, rank each treatment observation in ith block. So it is your block. Subject 1 is first block. How many blocks are there? 6 blocks are there. So you have to rank 3 observations, 1.21, 1.47 and 1.56. So only 3 observations. The task is extremely easier. You can see 1.21 is the lowermost value, so 1. 1.47 is second lowermost, so 2. And the largest value in this conglomeration of 3 observation is 1.56, so it should receive the rank 3. Similarly, get down to all of the observation, assign their ranks, but within the treatment. Clear? Now you can understand. Next also the second block, that will be 1.63 the lowermost, so rank 1, 1.85 second lowermost, so rank 2, 2.01 is the third one, so rank 3. You can just check on the fourth observation. You will see the first observation, which is a 2.43. It receives the rank 2. 1.98, it is the lowermost, so its rank is 1. And finally 2.64, it receives rank 3. Okay, so next task is to find out the column total. So the first column total, that is R1. What is R1? 1 plus 1 plus 1 plus 2 plus 1 plus 1, and it turns to be 7. Similarly, 2 plus 1, so 4, 6, 4, 5, 6, 7. Clear? So then rank the sum of the second column, sum of the ranks of the second column are 2, that is 12, and then R3, that is 17. So we are done on the computational part. Next we will find out the Friedman test. Clear? What is the test statistic? Summation Rj minus k into n plus 1 by 2. K is the number of blocks, n is the number of treatments, and you just figure out what is the value of q, and we have seen that q is 8.33, and already we have learned that q follows a chi-square with n minus 1 degrees of freedom. N is the number of treatments, right? So what is n here? How many drugs you are dealing with? 3 drugs. So 3 minus 1, that is the degrees of freedom of chi-square. So that will be 2.05, and chi-square tabular value, all of you are familiar of how to look to the chi-square table to fetch out the tabular value. I have already explained it beforehand. So, chi-square tabular value for 2 degrees of freedom and 5% level of significance turns to be 5.992. What is your Q calculated? 8.33. So, Q is bigger than the chi-square tabular value. 8.33 is bigger than 5.992, and we reject the null hypothesis. That means the probability distributions of 3 drugs are not same, or what you can write in either way round, that the medians of the 3 drugs are not the same, do not have the same effect on the subjects. Clear? So, that will be a more beautified expression to explain, to interpret your result. The same thing we can solve by R. Let me open my R window. Okay, so here you can see it's extremely easy. Writing the data is much needed, but in this case, as I have told, that you have to present your data in a rectangular array, so you know how to write a matrix in R. So, matrix in R is the syntax is like that: matrix bracket C bracket 1.21, means I am just writing all the observations. You have to mention the row number. Row number, n row is equal to 6 and by row is equal to true. What does it mean? That means when you are giving the values 1.21, 1.47, 1.56, then you have to read, you are instructing R to read these observations along with the row. So, 1.21, then 1.47, then 1.56. These will be the first row, followed by 1.63, 1.85, 2.01. That will be your second row. So, by row is true. That means you are instructing R to go through to form the matrix across the row. Row-wise reading is done. Okay. And one more thing, here you can see dimension name. Dim names means dimension names. So, what are the dimensions you are using here? You are using 3 dimensions, 3 treatments: drug A, drug B and drug C. As I told you, drug A, drug B, drug C, these are the qualitative character. You have to write the qualitative character while writing within C, while writing with this vector format within the quote unquote paraphrase. Okay. So, list 1 to 6 and drug A, drug B, drug C. Let me run this and you will have the idea how does your data look like. Okay, reaction time. Run this, otherwise you can see how nicely R has made your rectangular array. Now, just for your interest, you can have a rough check about how the medians of these 3 drugs differ by plotting the box plot. Okay. So, let us do the box plot. What is your visual interpretation? Just by looking at the box plot, you can see that the darker line, so this is the drug A figure, this is the drug B and this is the drug C. Look at the darker line positions and you understand that no longer the medians, darker line means the median of each group. So, no longer they are equal or they are very close to each other. Now, Friedman test, let us do that Friedman test. You will have that chi-square 8.33, which matches exactly what we have found in our manual calculation, 8.33, and degrees of freedom quite obviously 3 minus 1, that is 2, and look at the p-value. P-value is 0.0155. So if you fix your alpha as 0.05, then p-value is quite less with respect to 0.05. Clear? And since p-value is less than alpha, we can reject the null hypothesis, and that's what exactly we received while doing the same problem by manual exercise. Let us get to the PPT again for a post hoc analysis. After your null hypothesis is being rejected, just like the Kruskal-Wallis test, you can also find which pairs are different, for which pair your null hypothesis is going to be rejected. So in post hoc Friedman test, there is one common test called Conover test. You can perform Conover test, and Conover test is a post hoc test to Friedman test. For performing the test, we have to install the package PMCM R+ in your R Studio, and the R command is given there. Now you can see I have just snapshot this portion from the R Studio. You can also make a paste of this comment to your R Studio, and you will find the same output. Now let me explain this output a little bit. What you can see that after making that R command over the reaction time, because reaction time is our observations for the last example. So you are performing that Conover test over the reaction time. Now pairwise comparison using Conover's all pairs test for a two-way balanced complete block design. So my first point is, what does it mean by the balanced complete block? Balanced means equal number of observation in each row and column combination. And in our case, you have seen that only one observation is given in each of the cross section of row and column. Clear? Now, how many drugs are there? There are 3 drugs. So, how many pairwise comparison one can make? Drug A, drug B, that is one pair. Drug A, drug C, another pair, and drug B, drug C. So, the third pair. So, 3 pairs you need to compare. So, now just have a look over this. In this you will have drug A and drug B. The p-value, these are all the p-values. P-value is 0.045. If you are setting your adjustment at 0.01, then you will see that this is greater than 0.01. So, there is no difference between the median of drug A and median of drug B. Then drug A, drug C, look at the p-value which is extremely low. Clear? Extremely low. So, that means 5.6 into 10 to the power minus 6. So, you can claim that drug is the median of drug A is completely different from the median of drug C. Also, make a check with the drug C and drug B, the p-value comes as 0.045. So, the p-value, in fact, it depends on what is the alpha you are setting. If you are setting your alpha 0.01, then your conclusion will be a little different. And if you are setting your alpha as 0.05, then your conclusion will be another different spectrum. So, the p-value for testing the equality between the median of drug A and median of drug B is 0.045. P-value between drug A and drug C is very low. So, median of drug A and median of drug C are totally different. So, now you can be able to identify which pair actually differs. For that, your null hypothesis is rejected. So, that's all about the Friedman test. And I hope that you enjoy Friedman test, because most of the time when your distribution doesn't follow a normal distribution, as well as one more point which I missed to tell you earlier, that when the number of observation under each block or under each treatment is very low, less than 10, then also it is preferred to use the non-parametric two-way ANOVA. Thank you.